Hello everyone, and welcome to Bio-Inspired Robotics Lab. We do bio-inspired robotics. Bio-inspired robotics means that we're getting inspiration from the nature, from the biological organisms that are shaped through this long process of the evolution. For example, like birds, they are very efficient in flying. They can fly dozens of kilometers, relying upon a small amount of food. The cheetah is running very fast, again, relying upon a very small amount of food. One of other examples, like elephant trunk, it's multifunctional basically. The nose of the trunk, the elephant can pick up the fruit. The smaller fruit it picks by pinching. The bigger fruit it picks by suction. But the bigger things, the elephant actually lifts by the trunk itself. And we've got several questions about the trunk. Where is the trunk? You're talking about the trunk. So we brought up the trunk, and my colleague will introduce you an elephant trunk.
Right. Hiya. This is elephant trunk that I made today and yesterday. Well, basically is a series of pneumatic muscles connected together. So the way it works is that inside is actually a balloon, and outside it has like a mesh. So when you pressurize the balloon, it contracts. So therefore, it can change shape, like an actual elephant's trunk.
Yeah. So it's very exciting that after a short period of time we will have a complete trunk, and maybe at some point we will have an elephant also in the room. Yeah. So we also do some other bio-inspired parts, like for example human hand, which will be introduced in details by Fen. Please, Fen, take over the stream.
Here's an example of robot hand that we are making. So when a normal robot hand has a rigid body and a lot of sections, the motor between sections will actuate the fingers to make it grasp the object. However, in our project, our robot hand is first soft, and second, it has second passive. Passive. That means it has no actuators inside the hand, but it still picks up the ball successfully. It's because this kind of robot hand is inspired by a natural discovery that the behavior of animals do not only result from their brains, but also result from their interaction between their body and the environment. So the passive soft robot hand successfully pick up the ball because of its stiffness of the finger. But here comes to another question, that how does the robot hand know where the ball is and whether it pick up the ball successfully or not? Inspired by human tactile sense, we built some airbags on the surface of the robot hand, and when the surface contacts the object, the pressure of the airbag will change, and the data will be sent to the robot. Therefore, the robot will know whether it picked up the ball successfully or not, and then use this kind of knowledge to improve its successful rate by changing its stiffness.
And that's an example of soft sensors and why we might want to use soft sensors, which can be bendy, which can be flexible, which can be stretchable. And that's much more like the kind of sensors we have in our hands, in our fingers, in our bodies, and that we see in nature. That's much more similar than, say, a rigid solid sensor we might plug into a normal robot. So something like this might be one of those sensors. It's rigid, we can just plug it into some electronics, and in this case, if we do that, it'll tell us the humidity and it'll tell us the temperature of our environment just by reading out some numbers on specific channels of this sensor. But soft sensors can be much trickier than this. So I've got a soft sensor here instead, which has been 3D printed along the bottom of this inflatable stretchy finger made of a hydrogel material. And this sensor is to tell us how deformed the finger is. But because it's soft, it might not necessarily just bend. It might also bend and twist. It might bend, twist, and stretch. And just from this sensor response, we have to try and work out which of these many, many states this finger is in. And there's a few ways we can try and solve that problem. We can look at the sensor response over time, so we can see that it starts to twist, and so we know that later on it's going to be in a twisted state, or the same with stretching or bending. Or we can look back at a memory we have of previous deformations where we've known exactly what state the finger's in and we've known the response. And if we've got a huge database like that, we can essentially predict which state the finger's in now. To build up that database is pretty tricky, but that's what's going on another example over here. We've got a sensory skin which is stretched across, made of that same material, and can sense when it's being pressed, when it's being deformed. We're in the early stages of training at the moment. It's just learning how it responds when it's pressed in lots of different locations by this robotic finger. And later down the line, that finger won't be there, but it'll draw back on its memory of this moment to know where it's being pressed by something else when it's on a robot. And yeah, that's one use of this material. This material is also edible, it's biodegradable, and it's really easy to make, which we do up in our fabrication mezzanine. That's where Arsen is at the moment, so I'm going to hand back to him.
Thanks, David, for introduction and highlighting the importance of the fabrication process. Actually, fabrication is not that easy, and we are doing fabrication is basically in this area. We have two types of fabrication. The first type of fabrication is like by 3D printing. Like these days, we have like a wide range of materials, like from the rigid ones, like a plastic, for example. This I can we can like basically print like the molds and cast some things on it, or it can be like flexible, but it has its own limitations. Like in most cases, we also use the molding and casting the silicone or some other sorts of rubber in 3D printed cast, for example. And then in most cases, we need to have the combined approach. Like, for example, in this case, we have a rigid skeleton implanted into the silicone-based flesh and skin. The important thing about the sensors that David was mentioning, like there is a wide range of different sensors, but the main idea is to during the fabrication process to put this sort of strings into the skin of the robot. So when we can touch it or bend it, it can sense the strain signals and use it for some more complicated tasks, like Fan introduced the ball picking task or any other tasks. Sometimes we can make any material being a sensor, so that in this case, during fabrication, we can put some chemicals, making those material sensitive for strain or for compression. For the material that we will be using in this like demonstration scenario is hydrogel. It's like a gelatin. You can basically eat it, but by adding some material, some conductive material like salt, it can have ionic conductivity and it can be used as a sensor. Basically, when we have these kind of compounds, we can heat it up a little bit and we can mold it in this 3D printed shape. So we can have, for example, gripper, which will be used at the end of this demonstration by Ryman. But also another important thing, like using this material, we can basically sensorize any object. And this demonstration case will be provided by Fan Yi. Fan, please take over the.
Here is a demo of our sensorized globe. We print a kind of hydrogel on all the fingers of the globe. And this kind of hydrogel has ionic conductivity, and the electronic resistance of the hydrogel is very sensitive to the changes in their length and their area. So when we wear the globe and bend our finger, the resistance of the hydrogel will change because the length of the hydrogel changes. And in this way, we can sense the motion of our finger by sensing the resistance of the hydrogels on the globe. And in addition, this kind of hydrogel can be printed on other surfaces and used to sense other properties like humidity and temperature, which makes it very easy to customize. And then let's pass the turn to the OHMC.
Welcome to the Conservatory for Human-Machine Collaboration. My name is Ryman, and I'm going to show you some of the examples we have done here. Well, we have the kitchen robot first. We will come back to this guy. But first, we're just going to show you a little bit in a 360 degrees. One of the first one is a musician robot, which a robot that plays piano and basically kind of simulating a piano player with the soft fingers that some of the example you show upstairs. Another robot is a farming robot. This robot can be placed in a farm and can harvest lettuce, ready lettuce, so it can be ready to the market, from the robot to the market. And then the other robot is the foodly robot. So this robot is handling ready-made food and basically packaging them to the customer. So maybe one day you'll see one of these guys in a supermarket or in a food industry. So let's go back again where we started, where the kitchen robot is. So this is a kitchen robot. The robot has almost like a taste sensor. So this is conductive probes that they can measure the current in between them. And this can be put or placed on food, on top of food many, many times when the robot is cooking. So we could know what is the food taste like. For example, salinity measure, we could see the humidity and so on. So all these sort of measurement that we need from the food to understand how it tastes like. But also when the robot cooking food, we needed something, the gripper should be something more biodegradable, for instance, or not damaged from heat or so on. So we wanted something that matched the way that we could work with food. And that's where the gelatin gripper, and it's similar to what my colleague explained earlier, we have these gelatin's gripper that can be gripped to different foods and then can be eaten after. So let's show you something like what the robots would do and run this quickly. So if this is a gripper on the robot, if there's any object here that can grab it, food or vegetables or fruits or anything like that. And what we're demonstrating here really is just dipping the gripper in a chocolate fountain. And so it can be maybe more delicious. So what we can do is actually eat in it. So here we go. Delicious, dipped with chocolate, and can be eatable. Thank you very much for listening and really ready for your question. Thanks a lot.
So like you said, we do have time for some questions. So what I'm going to do is I'm going to bring everyone back on screen. So let's have Van back. Let's have Arson. And then as he finishes eating that bit of gripper, let's have Ryman as well. Okay, so we've got some questions here. Can you tell us how the actuator tasted?
Oh, that's a very good question. It's up to you how you can make it, how it tastes you want it, because you add all your own flavor. We flavored it with some gravy kind of flavor, so it's almost like it tastes like a lolly, but I don't think so. We are a good chef yet, so it doesn't taste that great yet. But we couldn't make it the way we wanted it, so it's all good with that. Don't worry about that. We still can make it a better flavor.
What do you wish you'd known when you first started this project? Now, I think this came through when we were talking about the sensors, the sensorized hands, the sensorized grippers. So I might take this question and say that it's always about where we put the sensors is the difficult bit to know. We still struggle with that now. Do we just cover something in sensors and maybe be very inefficient? Or do we place the sensors a bit more tactically so we've got fewer to work with and be confused by, but we have to get the perfect position, which is still a very difficult question to answer. So thank you, Claire, for that. Could we use our robotic hands or the soft sensors for implants? And I think I'll pass that to Arson. If you're happy to answer that, I'll unmute you there.
Yeah. It's actually, it's a very, very good questions that we wanted to cover actually. We know that like in prosthesis, for example, so we basically attach the artificial limb to the patient, and then basically patient doesn't really feel anything through this like artificial hand or artificial leg. And one of the priority research area is to really put the sensors into those prostheses and to convey this information to the human, so the human can feel it in a way it feels the original hand, like or in some signal that can be interpreted in the right way. So the user, for example, can feel that the object is like soft or hard, or for example, to feel some texture on top of the object, or some other things, like, or like feeling temperature, also very important when the user operates with some things in the kitchen, for example. Again, it's very very important and like priority research area right now in the bio-inspired robotics.
It's a good place to end the stream there. Thank you all for watching, and yeah, goodbye.